If you have ever tried to generate an image with dense text in it, you know the output usually looks like, well, alien hieroglyphics.
Oh, absolutely.
Welcome to AI Paper Podcast. Today we are looking directly at the Qwen-Image-VAE 2.0 technical report, which was published by the Qwen team on May 14th, 2026. Here is your 60-second summary. Right now, latent diffusion models are hitting a massive computational wall. Standard F8 spatial compression creates just way too many latent tokens for diffusion transformers, or DITs, to handle efficiently at native high resolutions.
Right.
So moving to F16 or F32 compression is the logical next step, but it typically destroys fine image details, especially text, and it completely ruins the diffusability of the latent space. Qwen-Image-VAE 2.0 solves this tripartite trade-off between compression ratio, reconstruction quality, and diffusability.
Yeah, they really did.
They achieved this by overhauling the architecture with global skip connections, expanding latent channels, and totally ditching standard KL and JAN losses in favor of Dino v2 semantic alignment. By pairing this with a massive synthetic text rendering pipeline, the performance gap is definitively closed. Their F16 model actually beats the best F8 models like FLUX.1 Dev in pure text reconstruction, and their F32 model remains legible where competing models just turn into blurry smears.
It is wild.
Okay, so that is the high-level summary. For the rest of our time today, we are going to unpack exactly how the Qwen team pulled off this huge engineering feat. We will explore the architecture, those highly debated training decisions, and the brand new OCR-based benchmark they built to prove their methodology works.
Yeah, it's a critical paper for anyone currently trying to, optimize high-resolution generation pipelines.
To really understand why the Qwen team pushed so hard for F16 and F32 compression, we have to look at the massive computational bottleneck we are all hitting right now. In modern image synthesis, the variational autoencoder, the VAE, compresses an image into a latent space. For years, compressing the spatial dimensions by a factor of 8, F8, has been the absolute gold standard.
Pretty much the default for everything.
Exactly. But suddenly, as we move toward native high-resolution generation, F8 is it's no longer viable.
No, the math of modern diffusion transformers makes F8 totally unsustainable for high resolutions. I mean, DIT scale quadratically.
All right, the O of L squared issue.
Exactly. The computational complexity is O of L squared, where L is the number of latent tokens. So if you were generating a 2K or 4K native image, an F8 compression simply leaves too many tokens. The sequence length becomes totally unmanageable.
And that quadratic computation becomes crippling, right? Not just for the training loop, but for inference speed, too.
Oh, yeah. It just grinds everything to a halt.
So pushing the compression to F16 or F32 cuts that sequence length down dramatically. But the paper outlines this tripartite trade-off that makes doing this incredibly difficult.
Yeah, it is a really tough balancing act.
Because when you compress the spatial dimensions by a factor of 16 or 32, you lose the high-frequency information.
Right. The fine-grained details just vanish, like the sharp edges of tiny text characters.
Right. They just disappear. So to fix that spatial loss, engineers naturally expand the latent channel dimension. I like to think of this like packing for a long trip.
Oh, I like this analogy.
Yeah, so you want to use a much smaller suitcase, right? That is your higher spatial compression, which makes a DIT's life easier. But you still have the exact same amount of stuff to bring. So to fit it all, you just cram everything in by expanding the hidden pockets inside the suitcase, which represents increasing the channel dimensions.
That analogy perfectly illustrates the third part of the trade-off, which is diffusability.
How so?
Well, when you pack all that complex high-frequency information into those expanded channels, the latent distribution becomes entirely unstructured. You have packed the suitcase, but it is a disorganized mess.
So it's impossible to find anything in there.
Exactly. When the downstream DIT tries to process that latent space, it struggles to converge. The network simply does not know how to unpack that disorganized data efficiently.
So packing that tiny suitcase without turning the contents into a mess requires a physical redesign of the VAE itself.
It does. You can't just tweak the parameters.
Right. And the first major architectural shift the Qwen team introduces is global skip connections, or GSC.
Yeah, this directly addresses the loss of high-frequency data during downsampling.
Because normally downsampling just throws that data away, right?
Basically, yeah. In a standard VAE encoder, aggressive downsampling naturally filters out pixel-level information. But global skip connections establish a direct shortcut straight from the input pixels to the deeper latent space.
bypassing the initial downsampling stages completely.
Exactly. They bypass it entirely.
Wait, but how do they do that without just making the spatial dimensions huge again?
They achieve this using a space-to-channel operation.
Okay, what does that actually mean in practice?
Instead of summarizing or pooling the pixels, which inherently discards data, they physically reshape the tensor. They trade spatial width and height for channel depth.
Oh, wow. So they are folding the spatial information from the high-resolution input directly into the channel dimension.
Yes, and the ablation studies in the paper demonstrate exactly why this is so effective. Compared to local skip connections, or having no skip connections at all, the global approach significantly accelerates training convergence.
Because the network gets a pristine high-frequency signal right from the start.
Right from the very first step. It is not trying to guess what was lost.
Okay, but wait. If we are expanding the channel dimensions to compensate for F16 or F32, and we are using these global skip connections to fold even more raw spatial data into the channels, don't we run the risk of just shifting the bottleneck? Like, we might save the DIT some compute, but we are building a massive computationally heavy VAE that takes forever to encode and decode.
That is a great point. And efficiency was clearly a major concern for them, which is why they deployed an asymmetric encoder-decoder architecture.
Asymmetric, so one is bigger than the other.
Exactly. The encoder is remarkably lightweight. During diffusion training, engineers have to encode billions of images to extract their latents, making encoding speed absolutely paramount.
Oh, right, because you run the encoder constantly during training.
Yes. By keeping the encoder lean, they maintain high throughput. The decoder, however, is much heavier. It is used less frequently during the training loop, but is solely responsible for turning those heavily compressed latents back into high-fidelity pixels.
So you invest the compute where it actually matters for quality without slowing down the training loop.
Precisely.
I also noticed they stripped out self-attention modules entirely. They rely exclusively on an attention-free, convolution-based backbone.
Yeah, no attention layers at all.
That stood out to me because attention mechanisms are, ubiquitous right now. Everybody uses them, but it makes perfect sense for throughput.
It really does. Self-attention requires activation memory that scales quadratically with the sequence length.
Just like the DIT issue we talked about earlier.
Right, so by ripping it out and using convolutions, where computational complexity scales linearly with pixels, they maintain fast processing times even for ultra-high-resolution inputs.
And did they lose quality by doing that?
Crucially, they noted no significant performance drop from losing those attention layers. The convolutions, paired with the expanded channels, had enough capacity to capture all the necessary representations.
Okay, so the physical architecture solves the capacity problem, but to ensure the downstream diffusion transformer can actually read this dense latent space.
To ensure the suitcase is organized, right?
Exactly. To ensure the suitcase is organized, they had to rewrite the loss function. And this is where they threw out two absolute staples of VAE training, the Jan loss and the KL divergence loss.
Yeah, that was a bold move. Dropping the adversarial Jan loss was a very pragmatic decision, really based on scale.
How so? Because usually Jans are what make the images look sharp and realistic.
Typically, yes, a Jan discriminator forces the model to produce those sharp details. However, the Qwen team realized that when training on billions of high-quality, heavily filtered images, the Jan just becomes redundant.
Ah, because the sheer volume of clean data does the heavy lifting.
Exactly. They rely entirely on L1 pixel-level reconstruction and LPIPS.
Right. And for those listening who might not work with it daily, LPIPS stands for Learned Perceptual Image Patch Similarity.
Right.
It uses a pre-trained network to measure the perceptual distance between images. So it evaluates how similar two images look to the human eye, rather than just mathematically comparing them pixel by pixel.
And combining L1 and LPIPS at the scale of billions of images provides more than enough signal to produce really sharp details. Dropping the Jan discriminator removes a massive amount of overhead.
Makes sense. It just simplifies the whole optimization landscape.
Right, and makes the training far more stable. Jans are notoriously finicky to train.
Yeah, the stability argument makes a ton of sense for the Jan. But dropping the KL divergence loss, that completely rewrites standard practice.
It really does.
Because KL loss is what regularizes a VAE, right? It forces the latent space into a neat, normal Gaussian distribution so the diffusion model can actually predict it.
Yeah, that is the textbook way to do it.
Yeah.
But the problem is that a Gaussian prior actively fights against the Qwen team's core solution for diffusability, which is semantic alignment.
Semantic alignment.
Right. To make this highly compressed latent space easy for the DIT to use, they align the VAE latents with the features of a pre-trained semantic encoder.
And they tested several of those, right? Like DynoV3, MAE, PE spatial. But Dynov2L proved to be the most generation-friendly.
Exactly. Dina V2L was the winner. And this is exactly where the conflict with KL loss occurs.
Because they want the latents to represent actual meaning, semantics, rather than just a random normal distribution.
Right. Semantic features in the real world do not naturally conform to a perfect Gaussian bell curve.
So if you apply a KL penalty to enforce that Gaussian shape,
while simultaneously trying to align the latents to a complex semantic manifold from Dynov-V2, the model is basically being pulled in two completely opposing directions.
it's fighting itself.
Exactly.
Yeah.
The KL constraint actively degrades the semantic alignment. Removing it entirely creates a much more flexible and meaningful latent space.
What I found particularly clever about their use of Dynov-V2 is that they did not align to the final output layer.
Oh, yeah. That is a crucial detail.
They aligned to the middle layers, which is interesting because the final layers of these semantic encoders are highly specialized for deep semantic understanding.
They are, but they can be spatially noisy and overly abstract. The middle layers, on the other hand, offer much smoother spatial maps.
So they capture the meaning but keep the physical structure intact.
Right. Those middle layers capture robust semantic meaning, but retain enough structural layout that it is just way easier for the VAE to align with them.
Didn't they try combining layers too?
They did, but the team found that trying to fuse multiple layers together just introduced unnecessary noise. Sticking to a single, optimal middle layer yielded the best results.
And how did they actually compute that alignment mathematically?
To compute this, they utilized marginal cosine similarity to match the direction of the features and marginal distance matrix similarity to preserve the relative spatial layout.
Okay, so that guarantees the latents encode not just what an object is, but exactly where it sits spatially in relation to everything else.
Exactly, which is huge for image generation.
Okay, so aligning the latents gives us a stable, organized foundation. But then comes the ultimate test for any visual model. Dense, tiny text.
The hardest part.
Yeah, reconstructing text at high compression is where most models just fail catastrophically. To solve this, the Qwen team utilized massive data curation, filtering billions of images for clarity, and they curated a specialized document corpus of academic papers, financial reports, slides, you name it.
Right. But the curation is only part of it. The real breakthrough is their synthetic data pipeline.
The synthetic pipeline. Okay, tell me about that.
The synthetic pipeline is what pushes the model over the edge.
Yeah.
They built a custom rendering engine to synthetically generate text documents as images.
And it handles different languages.
Yeah, it supports alphabetic text like English and logographic text like Chinese, which is important because they have vastly different structural rules and stroke densities.
Oh, for sure. A Chinese character has way more detail packed into a small square than an English letter.
Exactly. And they deliberately rendered these characters at tiny scales, ranging from 5 to 20 pixels.
5 pixels. I mean, forcing the model to capture multigranularity details at 5 pixels under F32 compression is an extreme stress test.
It is incredibly difficult.
But they couldn't just render black text on a crisp white background, right?
No, definitely not.
I feel like training a model exclusively on clean backgrounds is like training a self-driving car in an empty parking lot.
Yeah.
The moment you put it on a real street with pedestrians and complex shadows, it just fails.
Exactly. If you only train on clean backgrounds, the model fails to reconstruct text overlaid on complex, noisy textures.
Like trying to read a street sign against a background of overlapping tree branches.
Right. So the paper uses a technique called background-contained synthesis. By rendering synthetic text over random general domain images, the VAE learns to actually untangle those high-frequency text strokes from complex background noise.
And they introduced this data through a highly orchestrated, multi-stage curriculum, didn't they?
They did. They started with low-resolution general images to capture basic structures, then scaled up to 2K resolution.
And then they bring in the text.
Yeah. After that, they injected the real-world text-rich images and finally brought in the synthetic background-contained text data we just talked about.
What is fascinating to me about this curriculum is that while they introduced the complex text data, they simultaneously began loosening the strict semantic alignment margins we discussed earlier.
Yeah, that loosening is a very delicate balancing act.
Why do they have to loosen it?
Well, in the early stages of training, strict semantic alignment is absolutely crucial to ensure the latent space is highly diffusible for the DIT.
Right, to organize the suitcase.
Right. However, semantics generally care about the meaning of a word, not the exact pixel-perfect rendering of a specific font's serif.
Oh, I see. Dino V2 knows it says Apple, but it doesn't care if it's in Times New Roman or Arial.
Exactly. So by loosening the semantic margins later in training, the model is freed up to focus heavily on the high-fidelity reconstruction of those tiny text strokes without being overly constrained by the Dino V2 features.
That is so smart. Okay, so training for text is one thing, but proving the model actually learned it exposed a major flaw in how the industry currently evaluates VAEs.
Oh, a massive flaw.
If you rely on peak signal-to-noise ratio, PSNR, or structural similarity index measure, ESIM,
Which everyone does.
right? But you are basically just doing pixel-level math, and those standard metrics completely fail to capture actual legibility.
They do, because a tiny pixel error can cause a catastrophic semantic failure.
Give me an example.
Okay, if you have an image with the word orange, and the VAE reconstruction distorts one tiny stroke,
Right.
turning the E into an O, the word becomes orango.
Right, which isn't a word.
Exactly.
Yeah.
But pixel-level metrics like PSNR will barely register a drop, maybe less than half a decibel.
Because mathematically, the images are still nearly identical.
Exactly. But semantically, the text is completely ruined.
And since standard benchmarks like ImageNet or FFHQ barely contain any dense text anyway, the Qwen team had to build a completely new evaluation standard, which they call OmniDoc-TokenBench.
Yes.
It consists of roughly 3,000 curated, text-rich images across 9 complex categories. We're talking magazines, exam papers, academic posters.
Really dense stuff.
Right. And to measure success on this benchmark without requiring engineers to manually draw bounding boxes around every single word, they introduced a metric called Normalized Edit Distance, or NED.
NE is an elegant solution to the evaluation problem. It is really smart.
How does it work?
They take the original image and run it through an off-the-shelf OCR model, specifically PPOCR V5. They extract all the text as a continuous string.
Okay.
Then they take the VAE's reconstructed image, run it through the exact same OCR model, and extract that second text string.
Got it.
Finally, they compute the Levenshtein distance between the two strings.
Which measures exactly how many individual character edits you have to make for the reconstructed string to perfectly match the original string.
Exactly.
But when I first read that, my immediate thought was that OCR models make mistakes constantly.
Oh, all the time.
Right. Even on clean images, an OCR might confuse a lowercase r and n for an m. I assume that would unfairly penalize the VAE for the OCR's mistake. But the brilliance of this methodology is that they do not compare the reconstruction's OCR to a clean, ground truth text file.
No, they don't.
They compare the reconstruction's OCR directly to the original image's OCR.
That direct comparison perfectly isolates the VAE's performance. It's brilliant.
Because the errors cancel out.
Yes. If the PPOCR V5 model has an inherent bias and consistently misreads an RN as an M on the original image, it will make that exact same systemic mistake on the reconstructed image.
So those inherent errors just cancel each other out in the edit distance calculation.
Exactly. The only differences left are the degradations caused solely by the VAE's compression and reconstruction.
So running those pure isolated measurements reveals some substantial performance gaps. The baseline performance of standard F16 VAEs on OmniDoc-TokenBench is just poor. A model like Cosmos 0.1 CI16 by 16 collapses to an NED of 0.1547.
Meaning roughly 85% of the characters are completely mangled.
Right. Even the better baselines in the industry hover around 0.7 or 0.8. But the Qwen-Image-VAE 2.0 S16 C128 hits an NED of 0.9617.
Yeah, that F16 performance completely upends current assumptions about spatial compression limits.
Because it doesn't just outperform other F16 models.
No, it actually beats the state-of-the-art F8 VAEs on the market.
Including FLUS 0.1 div, right? Which scored a 0.9546.
Exactly. They're achieving superior text fidelity while compressing the spatial dimensions twice as much as FLUX.
And the extreme compression results at F32 are equally telling. Competing models at F32 like LTX Video or DCAE Sana completely break down on this benchmark, outputting NED scores between 0.07 and 0.57.
They literally reduce the text to illegible smears at that compression level.
But Qwen's F32C192 model achieves an NED of 0.8555.
Right. Retaining distinguishable character forms and clear word boundaries at a 4x spatial compression compared to F8. It proves that their architectural and training modifications are not just incremental tweaks.
It's a whole new paradigm.
The combination of global skip connections, DNO V2 alignment, and the synthetic text pipeline provides a fundamentally better way to compress visual data.
But to verify they truly solved the tripartite trade-off, they had to prove this heavily compressed, text-capable latent space was actually diffusible, right?
Yes. They tested this using downstream SID-T scalable interpolant transformers on the standard ImageNet 256 by 256 benchmark.
And how did it do?
The downstream metrics confirmed the latent space is highly optimized for diffusion. They evaluated the inception score, or IS, and the generative Fréchet inception distance, or FID.
And importantly, they measured the generative FID without classifier-free guidance.
Right. CFG is often used to artificially boost image quality, which can sort of mask underlying distribution issues in the latent space.
Ah, so taking off the training wheels, basically.
Exactly. By evaluating the raw, unguided FID, the data clearly shows that despite the massive channel dimensions required for F16 and F32, the semantic alignment strategy genuinely works. The models facilitate rapid convergence and deliver superior generation quality.
For the ML engineers and researchers listening right now, the utility of this paper is immense. Qwen has effectively proven that you can utilize extreme spatial compression at F16 or F32 to dramatically reduce your diffusion transformer compute costs without having to sacrifice fine text details or latent diffusability. You get the operational speed without the text smear.
Which is the holy grail right now.
Exactly. So I want to leave you with a final thought to consider as you build out your own architectures. If we are now capable of packing this much pristine, semantically aligned information into an ultra-compressed F32 latent space-leveraging global skip connections and middle-layered Deno features to keep everything organized, how is this going to completely rewrite the rules for native high-resolution video generation or even 3D world building?
It changes everything.
Right now, sequence length is the single biggest computational bottleneck holding those specific industries back. If we have finally figured out how to pack that tiny suitcase perfectly without breaking anything inside, the operational ceiling for generative AI just moved significantly higher. Thank you for joining us on this edition of AI Paper Podcast. We highly recommend pulling up the full Qwen-Image-VAE 2.0 technical report to examine the exact loss formulas, the ablation studies, and the full breakdown of the OmniDoc-TokenBench. We will see you next time.